recording so that we have a record of this. And yeah, thank you. Brittany and I were just commiserating about the idea that sometimes I forget to record these things and then have to redo the whole thing with nobody on board. Okay, so we're recording at this stage. So basically, and hopefully you had a chance to look at the PowerPoint presentations that are made up by Jeff Burton. Did you guys play those PowerPoint presentations and listen to the audio? Were you able to work those pretty well? By the way, Lorraine, you can type into the chat box to the lower right hand side of the control panel that comes up. And if you want to ask me a question or you want to respond to something or something like that, did you guys get a chance to play those PowerPoints? When you play the PowerPoint, for instance, tonight we're discussing Chapter 5. Each slide has audio that's associated with it, and you can actually listen to Jeff Burton. He's the author of the two texts that we're using, the workbooks that we're using, and you can listen to his play-by-play on each one of those slides. I'm going to go run through those slides anyway, so that we get a chance to just look at them quickly, because there's a lot of interesting pictures on those slides. But I'll leave it up to you guys to actually hear them. Did you guys get a chance to play them, Brittany, Lorraine? Oh, okay, no problem. All right, when you get a chance, I'm going to go through them, and just so you get an idea of what it looks like, you'll see on my screen what the effect is, presumably. Okay, so I'm gonna bypass that part of this, and I'm gonna go right on to some of the math and some of the examples and exercises that are in Chapter 5 that you might find a little bit challenging. Most of Chapter 5 is not very challenging, but they do start to get into the mathematics of designing and measuring ventilation systems. So, what's our objective for this semester? Our objective this semester is, number one, learn about local exhaust ventilation systems. That's our primary focus for the first 2/3 of this semester, and learn about it. Let me just log off my mail so we don't get interrupted. As I was starting to say, our objective this semester is learn about local exhaust ventilation systems, the components that go into building these systems, how they're structured, how they operate, and so on and so forth. By the end of this semester, even though you may not believe it right at this point, you guys are going to be able to design and build a local exhaust system from scratch that provides worker protection. You're going to know how to select all the components. You're going to know where to. I'm going to make sure you know where to go and buy them, and so on and so forth. How to size them, how to specify them, and when you're done and this whole thing is erected, how to test the effectiveness of the product that you've put together. Okay, that's really a core part of what we're going to learn how to do. The next part of what we're going to learn how to do very frequently for many of us is going to come up even more frequently, and that's how to evaluate the performance of a system that's already been built by someone else. And you're always, industrial hygienists and public health people, you're always going to be going into situations where if you work in a hospital, if you work in industry, and so on and so forth, where there is some sort of device to protect workers from a contaminant, and you may be called on to evaluate whether or not it's really performing, whether it's protecting those workers or not. So we're going to learn, part of learning how to design and build these systems is that you also learn how to evaluate the performance of an existing system. Is it really protecting the workers? The worker being exposed to these materials. Was it, for instance, was it designed correctly? Or is it a operational problem, maintenance problem, operational problem, a defective part, or just was not designed correctly, and so it never has a chance of even protecting the worker properly. And finally, to diagnose and correct shortcomings in these systems. In other words, identify what the problem is and then fix it. We're not going to learn all of that today, right? So I'm sorry about the scribbly. That's not, my handwriting is better than that, but I'm using I did this a little bit ahead of time here, so you wouldn't have to wait for me to write through it. But I'm using a little bit of one of these little graphics tablets on the side here, write this stuff. So it gives me an opportunity to actually work through some calculations, do some sketches and stuff like that. But it's kind of hard to use these to write very clearly. Okay, so I'm going to move on to the next slide. And I see we got Jonathan joined us too. Hi, Jonathan. I hope you can hear me and see me. You can type into the chat box on the right-hand side on your control panel. By the way, there's a little orange arrow near the top of the control panel. If you click on that, it moves the control panel out of the way so you can see your whole screen. If you click on it again, it brings it back again. Okay, I've got all of you muted so that we don't have to hear background noise and stuff like that. If you're using a microphone, you can ask me to unmute you, and you'll be able to, all of us will be able to hear you. If you want to ask me a question or send me a message or something like that, type into the chat box. You can direct the message either to everybody, which is preferable, so that I don't have to repeat the question if it's a question, or you can direct it to me specifically as a private message, a little drop down over there that you'll see, I'm sure. Okay, so getting back to this, let's go on to, here's our objective. Let's go on to the next slide. Okay, so this is from Chapter 5 of the Industrial Ventilation Workbook. And the first thing that they broach in this chapter is basically, we kind of skipped a chapter, didn't we? We went from chapter 1 and 2 and 3, which kind of introduced this whole idea of exhaust ventilation. We jumped from there to chapter 5. Chapter 4 is almost exclusively on dilution ventilation. Well, dilution ventilation is just simply the kind of ventilation you might have in an air conditioning system or HVAC system, where contaminants might get into the air, like in an office environment, and you can control them by taking a certain proportion of the recirculating air, dumping it outside, and replacing it with fresh outside air. You can take that same approach with any kind of contaminant. Problem is, if the contaminant is particularly toxic, or if the worker has to work in close proximity to the process that produces that contaminant, that's not really acceptable, because dilution ventilation means the contaminant gets into the air and the worker is inevitably exposed to it. Even if you have a very effective dilution ventilation and you manage to lower the concentration of the material, the worker still has some exposure. And if he's working right on top of it, his exposure can be pretty significant. Okay, so, and in the chapter, they ask you to list some examples of local exhaust systems that you may have in your own plant or somewhere that you worked, and so on and so forth. I'm going to just take a look at the chat box. I know that where I work, we have a lab hood. We also have we do a little bit of welding, so we have a movable exhaust hood and ventilation system that they can use for welding purposes. And we have some dilution ventilation in our plant factory, where they store a lot of chemicals and so on and so forth. Do you guys have any experience with like where you work? Besides lab hoods, have you come across other kinds of ventilation systems? You can type in no if you want. That way I don't stand here waiting for you to wonder if you hear me or not. Okay, good. All right. All right, good. So this is some new stuff for all of us. Uh, oh, okay. Kitchen. Wait, listen. That's a ventilation system. In fact, one of the students in a prior class was doing his. I'm not sure. I'm not really involved with students at the stage where they're getting ready to graduate into doing projects, but I guess they call, like, basically what used to be a thesis or a master's project. They call that a capstone or something like that nowadays, if I'm interpreting that correctly. And one student worked for the Department of Health, and it was his job to go around and inspect kitchen exhaust hoods in restaurants and food processing facilities. And they have to be carefully inspected, but the fire department requires inspection, because as grease and other materials build up inside the hood itself and the exhaust system and the fan, that's a potential for a fire. In fact, a lot of serious fires get started because somebody hasn't maintained an exhaust system for a kitchen properly. And he was doing his capstone on basically ways to evaluate kitchen exhaust hoods based on the size of the hood and the amount of air that's going through them and and measuring velocities and so on and so forth. So actually, that counts. It's literally, and in a place like New York City, where perhaps we don't have the manufacturing base that we used to have at one time or another, they are a significant contributor controlling fumes and grease and carbon monoxide and whatever else might be coming off of a process where you might be cooking or heating foods and so on. So yeah, that's perfectly legitimate. That's a local exhaust system. Okay, so I'm going to go. Let's move on here. Okay, so what are the major components of a exhaust system? Okay, well, basically, almost all exhaust systems start off with some sort of device that's intended to capture the contaminant, a hood. Okay, and we call all sorts of different things hood. In the case of your kitchen exhaust system, you have a burner, right? And burners creating heat and grease and fumes and so on and so forth. And you have a hood that's mounted directly over it with some grease catching screens and so on and so forth in the back. And the fumes, because it's warm air and hot air, it's rising up into the hood, and the fans allows it to capture it and pull it up and take it away. In other situations, the hoods may look quite different. If you have a tool, it might have a shroud on it with a piece of flex duct coming off of it to capture sand or grit or dust or whatever else might be produced by that process. Sometimes when you have a tank with a warm liquid in it or liquid in it like a solvent or something like that, they will have a hood that at the back of it has a bunch of small slots in it. And that'll be connected to ductwork, and you'll have very high velocity air at these slots. If you looked at it from the side, the hood might look something like this with a duct coming off of it, and there'd be slots in here. And that has a tendency to capture fumes that are along that surface and pull them away from a worker who might be standing or working over here. So it's called slot hoods. So there's all sorts of different shapes and designs of different hoods. We're going to be looking at references. For instance, the ACGIH, American Congress of Government and Industrial Hygienists, they have a standard manual on hood design and measurement. Okay, we're going to be looking at that as we move on in the semester to decide what type of hood that we might need for a specific application, and also to see how that hood should be designed, at what velocity of air it needs to capture particulate or capture gases, and so on and so forth. So we're going to use that as a reference as we move forward. Okay, so the next thing that we have is that we have ductwork. We have a hood. We need some way to connect it to a device that's going to exhaust the air that it's pulling along with the contaminant and exhaust that outside of the worker's environment. Okay, so that ductwork is going to go over to a fan. That fan is generating a negative static pressure. It's generating a suction to pull that air in. Okay, and we know that if we put a hole in this ductwork, it'd pull on the suction side of this fan, it would pull air in. We know that the pressure in there is lower than the atmospheric pressure outside of that ductwork. So we're pulling air through that hood. We're using that ductwork as a conveyance to the fan. And then from the fan is what's giving us the energy that's required to produce that suction, to produce that negative static pressure, and to discharge the air outside of the building up the stack. Okay, now, in order to protect the environment and protect the fan from some of these contaminants, for instance, if they're particulates, if they're fumes, particulates, it may not be legal to discharge these into the local environment. Also, if they're particulates, they may damage the fan in some way, right? Or they may clog up the ductwork, or get dirty, and so on. It's cause ductwork to get dirty and change the performance on this system. So typically, there is typically some sort of device to remove damaging or objectionable contaminants from the air before it's discharged outside. Typically, you'll see that between the hood and the fan, because it can then serve the double purpose of also protecting the fan. Okay, if I pause every once in a while, it's usually so that I can take a quick look, see if there's any questions or anything like that. Okay, so the fan is the device that gives us this energy to do this. Now, let's see if I want to go back to this next slide first. And before I go there, okay, so now on this fan, since we're on the suction side, the static pressure, right, is negative on this side of the fan. When I say negative, I mean that it's less than atmospheric. It's not like a vacuum. It's not, there's air there and so on and so forth. When we say it's negative, it's less than atmospheric pressure. So the air will tend to move towards where the static pressure is lowest. The fan is going to pull that energy in here. And then it's going to discharge it outside to the stack. Now, on the stack side, you'll know that this ductwork, right, is then going to be under a positive static pressure because you're pushing air through it. So imagine this, if there was a leak in there, it would leak outside of this ductwork. On this side, it would leak into the ductwork because it's negative static pressure. On this side, it would leak out of the ductwork because it's positive static pressure. Okay, so if I was going to design this ductwork, I might want to put round ductwork on one side and rectangular ductwork on the other side. Which side do you think we prefer to have the round ductwork? Do I got an opinion on that? Anybody decide whether it's more important on the suction side or the discharge side to have round ductwork? Let me give you let's see where we want to. Well, you got to remember that the air is always going to move. Same quantity of air is always going to move through these. Unless we change the cross-sectional area of the ductwork, the velocity is always going to be the same. So yeah, you might obviously for this, let's assume that it's going to be the same cross-sectional area, whether we're talking about round ductwork or rectangular ductwork. Yeah, I'm going to want round on the suction side. Why is that, Brittany? Right? Got a suggestion why? Just because you've seen it that way? Have you guys ever seen demonstrations where you can have somebody that walks on eggs? There's a guy named Steve Spangler. He does a lot of these, he works for a TV channel, I think, out west. And he's kind of like the science guy, like kind of a Bill Nye kind of character. And he does these various YouTube videos that are based on these news broadcasts, that these 5 or 10 minute demonstration. In one of them, he has people in their bare feet walk on raw eggshells. And the precursor to that is he has them take an egg and tells them to squeeze it carefully, wrap it completely with their hand, and then squeeze it as hard as they can. It's enormously difficult to break an egg by wrapping your hand completely around it, squeezing it really hard, because circles or spheres tend to be strong. You see arches in architecture going back thousands of years because ancient architects understood that this shape, the circular shape, is particularly strong. So what can happen is that particularly when you have a lot of suction, a very large negative pressure, you could actually collapse the ductwork, and it's a lot easier to collapse square ductwork or rectangular ductwork than it is to collapse round ductwork. Some of you, if you've seen square ductwork come under negative pressure, you may have noticed that it kind of buckles in. As soon as the fan goes on, you clunk, and you see it kind of buckle in a bit, right? So the real reason we want circular duct on the suction side is because it's much stronger, much more rigid than rectangular duct is in particular. On the discharge side, less of an issue. Okay, so we want to keep that in mind. So that's one element of design that we've learned right off the bat about these kind of systems. Okay, let's move on. And now, when we were talking about, we're just talking about suction pressure. Okay, so now here is a duct. Here's the hood end of it right over here. Oops, let me turn this on. Here's the hood end of it here. Air's getting sucked in. Here's the fan. We know on this side, the static pressure on this side is negative, right? This is under suction. And on this chart, if it continues going along here, the static pressure is positive, right? It says negative and positive right here. Now, let's say this duct continues along here, okay? What's the velocity pressure on this side? Is it positive or negative? Let's get a opinion on that. Velocity pressure is the pressure that's generated by the air moving forward. It's actually directly related mathematically to the velocity of the actual air. Okay, anybody want to guess about what's the velocity pressure on this side and this side? Is it negative and positive, positive and positive, negative? It's positive, excellent. It's positive on both sides. And is it, assuming that this is all the same size ductwork, is it higher on, is the velocity pressure higher on the suction side or is it higher on the discharge side? Okay, it's good guess. It's not it's positive on both sides. It's the same. The velocity pressure comes from the velocity of air moving through here. So the air is going to be moving at the same speed here as it's moving here, as long as you don't change the size of the ductwork. Now, if this ductwork expanded like this, the air would slow down and the velocity pressure would be lower on this side of the ductwork. But remember, velocity pressure is related to the velocity that the air is moving through here. So now we're going to 90% of design is related to static pressure. Why is it related to static pressure? Well, static pressure is basically stored energy for us. It's a way for us to produce the flow of air. So if this is a negative static pressure here, we have an environment where we can actually force air, induce air to come in here. Now, in a sense, that's stored energy, right? That's our potential energy. The actual velocity pressure, the pressure exerted by the air actually moving through here, is actually our kinetic energy, our energy that's being used. So they're really interchangeable. So static pressure is what gives us the energy that we need that can be converted into air movement. So static pressure is going to be what we're looking at most of the time. If we want to move air through here faster, I want that fan to generate more static pressure on the suction side so I can suck air into this ductwork. Okay, so now if I wall this off, right, my velocity pressure is zero because there's no air movement, right? If I blank this off so that or I put a gate or a damper in here, then there's no movement of air, even though the fan's running. But my static pressure is very high. You can imagine that when you put your hand over a vacuum cleaner hose, right? There's no air moving, but the suction on there is enormous, right? Because you blocked it off, right? So all of the energy now is potential energy. That's static pressure. Okay, so when you take it off, some of that static pressure is changed into actual useful kinetic energy where the air is actually moving through that hose. Okay, now that hose introduces some losses of energy because the air when the air's not moving, it's not being subjected to friction. You're not losing energy to friction as it moves through the hose. However, when you actually have air moving, then you actually have some frictional losses. In other words, the static pressure at one end of that hose is going to be different than the static pressure at the other end of the hose, even beyond the right at the opening, even a few feet in from the opening versus 20 feet away. Static pressure, you're going to lose static pressure as it goes through there because you're losing energy to friction as the air moves through there. And if you can imagine, the faster the air is moving, the more you lose to static pressure because that static pressure is being converted to velocity pressure and you're losing energy to these various losses. Okay, so now when we measure this, so static pressure is going to be a big part of our design because that static pressure is going to determine how fast air gets pulled into our hood at this end. If the static pressure isn't high enough, well, then we won't have the velocity that we need to capture the contaminants at the hood, right? So in order to size the fan that we need, we have to have that fan sized so that it gives us the static pressure we need back here. But wait a second. What if we have a lot of ductwork and a bunch of turns and a filter and so on and so forth? We're going to lose some of that static pressure as we go through here. So in order to make sure we have the static pressure we have here, we have to calculate all of the losses so we know how much static pressure, what kind of fan we'll need, and what kind of static pressure it can deliver when we specify it. So that's a big part of the game here is we got to figure out how to make sure that we maintain enough static pressure at the business end of this thing, at the hood, and how we have to design it and put it together so that we actually deliver that static pressure, and as a consequence, the velocity of air getting sucked in, the capture velocity that we need at the hood. So that's important to us. So now the way that we measure this and check this is by actually measuring the static pressure at various places on the ductwork, after the fan, before the fan, and so on and so forth. In order to do this, we use a very simple device called a manometer. Now, a manometer can be as simple as a tube with water in it. Okay, so for instance, here we have a tube with water in it. Let me turn that off. Here we have a tube with water in it. And in this tube with water, if this were not connected to this ductwork, well, that tube, I'll open this up over here so you can see it, I think. If it's not connected to anything, let me see if I can't select this. Here we go. Make this a little bigger. If it's not connected to anything, well, what we have is the atmospheric pressure pressing down on this side, atmospheric pressure pressing down on this side, and the two ends of this tube are going to be exactly the same level. So now if we connect one end of this, like for instance, the right end of this, to the suction side of the ductwork, well, and right up against the edge of the ductwork, so we're not actually blowing into this tube, the air is passing over it. We're not actually blowing into it, which would, we would also be measuring some of the velocity pressure as well. Just on the side of the ductwork, we'd measure the suction that ductwork has, and the levels would change. The suction would be strong enough the stronger that the suction is, the further it would be able to pull this water up into the ductwork. So the difference in the height of these two represent how much suction that we have. So in this case, we have sufficient suction to increase the height of this column of water by 4 inches. Went down 2 inches on this side, 2 inches on this. So it's actually supporting the weight of 2 inches of water, that's suction. So we call that 4 inches of water gauge, or in other words, the static pressure is minus 4 inches of water gauge. Okay, I say water gauge because gauge means that you're comparing the pressure to what atmospheric pressure is. If I said, if I was interested in absolute pressure, well, that's another thing entirely. Absolute pressure is going to be, well, let's see, atmospheric pressure is 14.7 pounds per square inch. That's enough pressure, enough energy to support 407 inches of water, or 29 point something millimeters of mercury, right? If you had a barometer, for instance, that's the energy that you get. That's the weight that you get from the column of air that's above us. That's the weight of that air. So now we don't sense that as weight because it exerts its pressure like static pressures want to do in all directions on us, right? So now really when we measure a difference of 1 inch in this water column, that 1 inch means that inside the ductwork, the pressure is really 406, equivalent of 406, the weight of 406 inches of water versus 407 inches of water on the outside. But we're ignoring that, and we just measure that 1 inch of static pressure as the weight of water. So we simplify this whole thing by just looking at the difference between those two. So a manometer can be as simple as a inverted tube with water in it. Okay, here's another example of it. Right, so here we go. Right, okay, it's colored blue, so you can see it. Obviously, this tube is on the suction. The left-hand side is on the suction side of a duct, perhaps. Or it's also entirely conceivable that this other side, the right side, is on the discharge side of the fan, side of the fan on the duct, right? So it's pushing air. The air is pushing the water down, and if this side were just exposed to the atmosphere, it would be allowing it to rise, and we'd have the difference in height of these two things is the number of inches of positive static pressure we have downstream of the fan. Keep in mind that typically the way we would use this as a simple manometer would be one side or the other would be open to the atmosphere. Okay, so we're measuring the difference between the two. Okay, just to give you an idea, You can also have industrially, if you went on to looked at an air conditioning system, you'd see it as a gauge, simple gauge. This just simply uses a spring. So it pushes against the spring, and the spring either reads in PSI, pounds per square inch, or it may, in HVAC systems, it may actually read in inches of water. Okay, and with HVAC systems, it's easier to work with inches of water because the pressures that you're dealing with are smaller than they would be in, say, water systems or something like that. You can have systems like this that use digital devices to indicate the static pressure and the velocity pressure. We'll have some of those as well. And finally, I just wanted to show you this one here. This is called an inclined manometer. This is literally exactly the same thing as you might see that there's an opening up here that's connected to this tube with red liquid. There's an opening here that's connected to this tube with liquid. Since they're both open to the atmosphere, this end and this end are both open to the atmosphere, well, right now it's balanced at 0. This entire column represents 1 inch of water. The height here is 1 inch above the height here. If you were actually looking behind that, this would go up here, and there would be a little reservoir here that is level with this side, right? And then go up to here, right? So this measures 1 inch of water. If we connected this side, if we left this side disconnected, and we attach this side to the discharge side of a fan, right? Well, the static pressure is positive, so it would push in here. It would push this column of water down, right? Until let's say it pushed it all the way down to this 1.0, right? That would represent 1 inch of water that it displaced. The reason why we use a device like this is that it's difficult to measure easily 1 inch 1 inch versus half an inch plus quarter of an inch versus 0.6 inches. It's difficult to measure that easily. What this does is it inclines that 1 inch so that this entire scale represents 1 inch of water. So if I were looking for, it would be much easier for me to discern half an inch of water gauge versus 6/10 of an inch of water gauge. Of course, if I put this side, if I place this side on the suction side, left this side open to atmosphere, the same thing would happen. It would get pulled down here. And if I made a mistake and put the suction side on this side, then this liquid probably just wind up getting sucked out of here entirely. Or the other way around, put the discharge on here. So we're actually going to play with some of these instruments next week. Okay, I'm hoping that what we can do is at the start of the session next week, we go down and we meet in the lab in the basement. It's C014, the environmental lab. Some of you guys have been in there before. We meet in that lab, and we have taken an opportunity just to play around with some simple measurements on operating duct work, mainly manometers and so on and so forth. So we can start simply. If it's comfortable down there, maybe we'll just stick around. And in fact, I'll probably go down there to get started setting up at about 7:30. If anybody gets there early, they can join me and help me set up. Based on the attendance today, I wouldn't count on that, but however, I'm hoping that with that with the generating a little enthusiasm by getting a little hands-on work and stuff like that, that maybe I'll catch you guys in just maybe 15 minutes early, and we'll set up down there. If it's comfortable there, we'll just stay there. So I'll make an announcement assuming we can get into the lab. I'll make an announcement about that later on in the week to remind you and where to go, and we'll post a notice in case you forget and you go up to the regular room. Okay, so let's move on to the next part of this. So manometers, they're an important measurement device for us because we're really interested in static pressure. Static pressure really gives us a clue as to how effectively we're going to be able to move air through this system. Okay, so let's take a look at this typical hood system that we were dealing with before. And this time let's start at the fan. At this fan, we have a nice big fan with an electric motor on it, is spinning. Maybe it's a centrifugal fan, maybe it's an axial fan, doesn't really matter to us right this second. But we have a fan, and here's our electric motor, direct drive it looks like here rather than a belt or something like that. But here's our fan. That fan is pulling air in this direction and pushing it out this direction. Okay, so now I noticed that right here at this point, very close to this fan, the static pressure is negative 3 inches of water. This fan is pulling a large suction. Okay, we get negative 3 inches of water suction here. So now what happens is as we move back through this ductwork to our hood, we encounter frictional losses as this air is actually moving through here. And as we move back here, we can measure how much those losses are by actually using our manometer and measuring the static pressure at various locations. At this location, we measure 2.6. We lost 0.4 inches of water, suction pressure, water gauge, to this distance from here to here. What do you think it is about this ductwork that caused us to lose a significant amount of suction between the fan and this point right here? And we got an opinion on what might be contributing to that you can see in that drawing, right? Curves, elbows, right? Because the air we have friction in the ductwork, but then when you get to these elbows, it really messes things up, right? Because it bangs against here, and you lose a lot of energy to going around curves. We got 1, 2, 3 of them, to get to this filter, to come from this filter actually. Okay, so we lost a lot of energy to these curves, and we're going to talk about ways to predict how much energy that we're going to lose to these curves, knowing the diameter, radius of these curves, the size ductwork, the velocity air that's moving through them, and so on and so forth. So we're going to be able to, maybe before you build this thing, we measured this, for instance, we measured this after we built it, but before you built it, be able to predict what that static pressure is going to be, so we're not caught by surprise. Okay, so this is 2.6. Now over here, 1.6. Static pressure is down to 1.6. Just between the inlet and the outlet of this filter, which is not unusual because this may contain a media type device, so the air's got to go through a filtration device or something like that. So we've lost static pressure to this filter. So devices like filters and air cleaners and so on and so forth can introduce some static pressure losses. Then we have a long run of ductwork, a single 90-degree elbow, and back here we're down to one. Back here to the point we're connected to the hood, we have a remainder of negative 1.2 inches of water. Okay, so now if we can predict the velocity here, and we know the static pressure, we can predict, depending on we can go to the ACGIH manual. We can then say, well, if we want to measure the velocity here, we can predict that based on knowing this information about the hood and about the static pressure and the velocity pressure at this point and the rate of air movement at this point. We can predict what the velocity would be on that particle, and we can decide whether or not that's sufficient to capture this contaminant. Right? So why is this all important? This is important to us because if this is what we need at this point in order to capture our contaminant, then we have to make sure that we design the ductwork, choose the fan, and so on and so forth. So it's sufficient to give us what we need at that point. This is the business end of this whole thing. The rest of this has to be designed to support that. So it actually does actually capture the contaminant when we're all done. Now on the discharge side of it, static pressure is +1. And then it goes up here, and it's by the time it reaches the top, static pressure is plus 0.05. Notice it's dropping because, for the same reason, frictional losses in the stack. This stack could be very high. In the PowerPoint, if you play the PowerPoint and listen to it, Jeff Burton talks about how this stack has to be at least 10 feet above the roof level or any adjoining structure that's within 50 feet, particularly if that adjoining structure includes, say, openable windows or air intakes or something of that nature as well. So this stack might be very, very tall. Anybody know what this device is up here? The little triangle that looks like that's up there. We think you got any idea what that might be on the stack at the very top of the stack? That's a rain cap, right, Jonathan? Thank you. That's a rain cap. And rain caps are there to keep rain out. Okay, you normally don't want to see those on exhaust systems, because if you can imagine, you're pushing air up here, and bang, you run into this device right at the top of this thing. Does two things. It reduces your static pressure. It introduces a loss, right? So it inhibits air moving through this fan and reduces your static pressure on this side. And in addition to that, it hits the air with the contaminant or whatever remains of the contaminant, hits the rain cap and gets directed back downwards, right? Which kind of defeats the purpose of putting it so far up, right? So rain caps, when you play the PowerPoint, you'll see that Jeff Burton is not a very big fan of rain caps. And if you look at exhaust systems, usually you'll see some other kind of accommodation to keeping rain out of it, or dealing with rain, rather than a typical rain cap like you might see on your furnace or something like that. Okay, let's move on. So that's the deal. We need to design this so we get sufficient static pressure to support the suction that we need at that hood. Okay, so how do we do these calculations? How do we calculate this stuff? Well, here's our basic formulas that we covered in the first couple of weeks of the semester. We're only up to week 3, right? Seems like we've been doing this a little bit longer anyway, but we're only up to week 3. Okay, so what are these formulas telling us? Well, first formula, Q is equal to V times A, right? The amount of air that you're moving is equal to the velocity times the cross-sectional area. So if you have a round duct that has a 1 foot squared cross-sectional area, right? And you're moving air at the rate of 10 feet per second, right? Well, how much air are you moving through there? Well, it's V, the velocity is 10 feet per second, times 1 foot is, let's see, 10 times 1 is 10 feet. 10 feet, 1 foot squared, 10 feet per second is 10 cubic feet per second. Now we multiply that typically by 60 because we usually deal in cubic feet per minute, CFM. It's important that we keep track of the units. A lot of these various constants and formulas that we're going to be working with, for instance, like this number 4005 we're going to talk about in a second, that number is based on knowing what units that we're going to be using with that formula. For instance, we're talking about for the velocity pressure, and so, well, what measurements we're going to use for velocity pressure? As it happens, for that number 4005, we're dealing in inches of water, just as we are with most of the other work that we're doing. So for the most part, you and I are going to be working in US measurements or English measurements in feet, cubic feet, minutes, and inches of water most frequently for duct systems. Okay, so but we will occasionally divert over to international units, metric system units. In that case, if we were working with metric units, the velocity by pressure might be millimeters of water, right? So that velocity pressure, we need to put that into that formula, millimeters of mercury, but it wouldn't be 4005. It would be a different number that's specific to the use of the international units. Okay, so we would want to be mindful of that. We're usually using US units. Occasionally, we're going to come across a problem, and it isn't always there. Even the PowerPoints that Jeff Burton has, he kind of in some spots it's a little easy to make an error there, but we're going to be reminding ourselves over and over and over again. Anybody remember what DF stands for? Okay, velocity is equal to 4005 times the velocity pressure. The actual speed that the air is moving is equal to 4005 times the velocity pressure in the inches of water. This comes out to feet per minute, right? It's automatically corrected for by the using inches of water for velocity pressure. Anybody remember what the DF stands for? Let me get back here. Opinion, what does that DF stand for? Let me put it to you this way. Almost most of the time, when we're working here in New York City at sea level, at standard temperature and pressure, that D is going to be equal to, that DF is going to be equal to 1. That's a fact, right? Density factor. That's what that stands for, right? So most of the time, we can forget about this. And this 0.05 means the square root of the velocity pressure is what we're working with. Okay, so this formula tells us what the velocity of the air, what speed the air is moving at if we measure the velocity pressure. How do we measure the velocity pressure? I'm going to have a duct in here, and I know I measure the static pressure by putting a tube over here and seeing how much it diverts water, right? So on this side, let's say it gets pulled up a little bit. So the difference in height here is my static pressure on the side. Static pressure operates in all directions, down, up, left, right, all at the same time, kind of like the air in a balloon, for instance, or the air around us in the atmosphere. That's static pressure too. It's not moving unless there's a wind or something like that. Now, to measure velocity pressure, we have to put a tube in here and point it into the flow of air. And then I'm going to put another U-tube over here and fill that with water. Okay, and I'm going to, for the moment, say that there's a change in height. Let's say it's a change in height like this, right? Let's say it's something like this, right? The velocity, maybe the air's moving through there really fast, that pushes that down and so on and so forth. Is this the velocity pressure I'm measuring here? Anybody got an opinion on that? Am I measuring the velocity pressure by doing that? Any opinions? Looks like it, right? It's measuring in other words, you blow in there and the speed of the air pushing in there is pushing that water down there. The faster the air is moving, the more it displaces that water. You guys think that's the velocity pressure? Well, it's not the velocity pressure I'm measuring. What am I measuring there? Anybody want to hazard a guess? Total pressure. Excellent. Great. Okay, the reason why it's total pressure is because not only do I have the air that's moving in there that's pushing against this, but I also have the static pressure pushing against this, which operates not just down this way, but also this way or that way, along with the velocity pressure. Okay, so now that brings us to this formula. The total pressure is equal to the static pressure plus the velocity pressure, and that's what this tube is measuring right here. Well, now keep in mind that if I'm on the suction side of the fan here, the air's moving that direction, the static pressure is negative and the velocity pressure is positive. So the total pressure could be positive or negative, depending on which one of these is greater. Usually, I think most of the time you're probably going to be negative if the air's moving through there, right? So we have to be a little bit careful about, well, what is this? The real strength of this formula is if we know any two of these, we know the other. If we know the total pressure and we know the static pressure, right? Well, then total pressure minus the static pressure is equal to the velocity pressure. So if I need to find the velocity pressure, I can measure the total pressure, right? And subtract from it the static pressure. So the velocity pressure would be whatever the total pressure is minus the static pressure. Actually, be minus, and then a negative number would be adding that number, the number of inches of water to the total pressure to get the velocity pressure. But the real point here is that with this formula, if we know any two of these, we can calculate the third. Similarly, if we know what the velocity is, we can calculate, if we know what the velocity pressure is, right? If we know what the velocity pressure is, we can calculate the velocity of the air. If we know what the velocity is, right, we can calculate the velocity pressure. Well, how would you do that? Well, divide by 4005 on both sides and take away the square root here and take this whole thing and square it. And that's what the velocity pressure is equal to. It's equal to the velocity of the air over 4005 and the whole thing squared. Okay, so we can use these formulas in various ways to effectively learn about the pressures and the movement and so on and so forth of this air in this system. Okay, pretty interesting stuff, right? Okay, and once we really start applying this stuff, you're going to feel like Superman. You're going to be so confident in designing these kinds of systems or understanding or gaining an understanding of these systems.